Hello everyone, welcome back to the final talk of the day. We have a pre-recorded session with Dijana Oreski on intelligent systems for automatic selection of machine learning algorithms in social sciences. Dijana will be joining us after the session to answer all your questions, so feel free to ask anything in the live stream chat and we will address it in the Q&A afterwards. Let's play the clip.
Hello, good afternoon to everyone. Greetings from Croatia. My name is Dijana Oreski. I work as assistant professor at the Faculty of Organization and Informatics, which is part of the largest Croatian university, University of Zagreb. And here I will deliver a talk entitled Intelligent System for Automatic Selection of Machine Learning Algorithms in Social Sciences. In the introduction, I would just like to briefly explain my research background and field of research in order to explain motivation for this work. I have obtained my PhD in the field of data science, developing new feature selection techniques and trying to find relationship between feature selection technique performance and characteristics of the data sets on which they are employed. Since I work at the Faculty of Organization and Informatics, which is part of social sciences, I have dealt with lots of social science data. And I have learned that machine learning approaches are still relatively little employed at the social sciences field. And this is motivation for the research project that I'm principal investigator, and the part of this research, which is ongoing research, I'm going to present here today. Just a little bit of off topic. This is our Faculty of Organization and Informatics, which is situated in the center of beautiful city of Varaždin, and this picture is taken a few days ago, which is a window view from my office, and it is another motivation to do the research. So back to the topic. This talk is actually divided into 3 parts. In the first part, I'm going to try to answer the question why this research is important and why it is valuable to research. In the second part, I will give the answer what we are doing and what are the main components of the research. And in the third part, I will explain how did we do what we did and how we will do in the next few years of the project. As we all know, there is a huge number of machine learning algorithms developed and applied in various domains. Such algorithms have crucial role in harnessing the power of big data and huge amounts of data that are produced today in the digital age, where each our click is somewhere stored. The application of such algorithms, especially for non-analytics experts, is really complex. It's time-consuming and it is iterative process. And there is a need to automate the selection of algorithms in order to facilitate development of the predictive and descriptive models. So the question to be asked is which algorithm is best to use in certain situation in a particular domain at a dataset of particular characteristics. The field that is developed to answer this question is called meta-learning field, and it is based on the no free lunch theory, which says that there isn't such technique or machine learning algorithm which would be the best for all situations, for all data sets, for all domains. So the idea of meta-learning is to learn from previous experience on a data-driven way. And we quantify meta-learning as process of learning from previous experience, which is gained during applying various algorithms on different kinds of data. Meta-learning techniques have been introduced, and there are several meta-learning techniques developed so far, and they're shown to be effective mechanisms to tackle this problem. We can do the categorization of meta-learning techniques, and here I use this categorization into three categories, into three groups. First group is based on learning from model evaluation, and we have three approaches which is part of this group: relative landmarks, surrogate models, and worm-started multitask learning. The second group of meta-learning techniques are approaches based on learning from task properties, and we have two main approaches here, using meta features and building meta models. And third approach is learning from prior models, and here we have two approaches: transfer learning and few-shot learning. In this project, we are focused on second group, learning from task properties, where we are using meta features, and based on those meta features, we are developing meta models. So few words about this approach to meta learning. Those techniques have been based on learning from task properties, and they are using so-called meta features to characterize particular data set. The basic idea of this learning is that each task is characterized by a feature vector, which consists of certain number of features. Information from a past task can be transferred to a new task based on similarity between the tasks. So similarity can be calculated based on some of the distance measures, and meta-learner can be trained on the feature vectors of prior tasks, along with their evaluations to predict the performance of configurations. As we saw, meta features and meta models are in the heart of this approach. And in the next part of a presentation, I will talk about different meta features. And in the practice, the selection of best set of meta features is also dependent on application and domain. And in the literature so far, there have been developed several approaches to classification of meta features. Here, we are using this approach, which consists of 6 groups of features, which are called simple measures, statistical measures, information theoretic meta features, model-based meta features, landmarking meta features, and clustering and distance-based characteristics. Let me just briefly explain each group of meta features. First one, called simple measures, or also called general measures, are measures that are easily extracted from data. As you can see here, in the table, where is the list of measures which are part of this group. There are number of attributes and their relation to number of instances, types of attributes, and relation of categorical and numerical attributes, number of classes in the attributes, number of missing values, number of classes, and some kind of relations between those measures. So they are simple or general measures. The second group are statistical measures, and as their name suggests, those are measures that capture statistical properties of the data. So they explain data distribution and distribution indicators such as average, standard deviation, correlation, and those measures are only for numerical attributes. As you can see from the measures, there are correlation, mean, geometric mean, maximum value, median, minimum value, correlation, outliers, range of the attributes, and so on. Third group of measures are informatic theoretic meta features. Those measures are based on discrete attributes, and they are based on calculating the entropy. As you can see here, they are based on entropy and the mutual information that is gained through the attributes. The next group of meta features are model-based meta features, and those meta features are extracted from a model induced using the training data, and they're often based on the properties of decision trees. As you can see by the names of features, those are number of leaves, then the number of branches, nodes per attributes, nodes per level, depth of the tree imbalance. So they're often based on decision trees. The next group of measures are core landmarking meta features, and those measures use the performance of simple and fast learning algorithms in order to explain the data set. The algorithms used here must have different biases, and of course they should capture relevant information with low computational costs. So there are some discriminant approaches, linear approaches, such as discriminant analysis, naive bias, and some approaches based on simple algorithms of neural networks. And we still have another group, clustering and distance-based characteristics, which are based on clustering and calculating distances and number of clusters. So meta features are the basis for developing meta models. In the process of developing meta models, the aim is to build a meta models that learns relationship between those meta features of prior tasks. So for the new task that we are dealing with, given the meta feature for that task, the meta model is used to recommend the best configuration. Also, meta models can be used to rank a particular set of configurations, and here we can apply similarity measures on the meta features of prior tasks and predict the top tasks that are similar to a new task, and then do the ranking based on configurations of these similar tasks. This approach gives us an indication of how good or bad this configuration can be, and whether it is worth evaluating it on a particular new task or it isn't. As saw in the previous research, data characteristics do really have impact on the performance of machine learning algorithm. And here I have emphasized few of the researchers which have developed some kind of matrix to evaluate the ability of machine learning algorithm to characterize different data sets. And they have used those matrices to find appropriate technique for a new classification problem. And in the next part, which is actually the crucial part of this presentation, I will explain and talk about specific domain, which is data from social sciences, and to be more specific, from the two parts of social sciences field. And I will try to give a brief explanation of specific characteristics of the datasets that we have explored so far. As I said, this is research which is just started, so we are in the initial phases, and the intelligent system which we will develop at the end is just at the beginning, so we have conceptual framework that I will show here. So on the one side, we have really growing interest among the machine learning scientists in topics which are traditionally like social science topics. And also we have a high level of increase in the volume of data and social science data which are available to our researchers. So awareness of applying machine learning models in social sciences is really raising. So here we are dealing of some kind of conjunction of big data and machine learning in the field that really needs high level of human understanding. Why social sciences are in the focus of this research? I have talked about it a bit in the introduction. So everyday social activities are influenced by digital systems, which generate huge amounts of data, and availability of data sources and development of algorithms and tools for data collection really does improve social science research, since recording on some phenomena that were previously unnoticed or they're even known, they even didn't exist, today is enabled. So such data are social data because information systems are complex, are dynamic, and they consist of digital technology on one side and social interaction on the other side. So this new paradigm really transforms a landscape for socioeconomic policies and research, and imposes new paths for business management and decision making. And identifying such data sources and how to treat this data and analyze it is really basic question to generate as much value, as much knowledge as is possible for organization in order to improve decision making. However, there isn't a specific recipe or specific flow for social and economic predictive analytics has been proposed yet, and this is necessary because socioeconomic data have particular nature, which have important components of uncertainty and human behavior, which is very particularly complex to model and to develop predictive models. And because of the great benefits that can be derived from the use of big data, in order to predict economic and social changes, this topic is really valuable. Integrating machine learning concepts in the social sciences have been slow because machine learning algorithms and social science data have very often tend to be in different corners, and different units of the path, and there are mechanisms to bring them together. In this talk, focus is in two social science domains, education and business, because if we take a deeper look at those two domains, they combine are forming a whole. And types of influence, which include business using the outputs of school, supplying inputs to school, shaping educational policy at various levels, and also distributing wealth in a ways that really directly and indirectly affects education. So this is the reason for using these two and focusing on these two domains. Regarding the business domain, our base is so-called Global Entrepreneurship Monitor database, which is valuable source of information on entrepreneurial activity. GEM database is really extensive and imposes specific challenges to data analysis. In some of the previous researchers, as a path for future research, authors identified that there is no systematic analysis of relations between dataset characteristics and methodological capabilities in this particular entrepreneurial domain. And of course, this imposes its specifics. Also, researchers of entrepreneurial activity should take into account that they are dealing with rare events. One value of dependent variable is really more frequent than the other value. In the machine learning, it is called class imbalance problem, and it is really specific for this area, and we need to find the best approaches to deal with such a problem. So there are only some open questions which serve as a basis for setting up goals of this research. just a few words about GAME database. So GAME collects internationally comparable data on entrepreneurial activity in more than 50 countries in the world. This database is really unique because there is no other source of comparable data on entrepreneurship from so many countries. And unlike existing statistics from the national levels, GAME database captures all kinds of entrepreneurial activities, and also they capture startups efforts which are at very early stage of their work, as well as new and established businesses, which is also their advantage. In the education field, there are data, of course, from elementary to high school and to higher education, and students' data is generated, and based on this data, academic performance could be predicted, which is valuable for all levels, for the students, for the teachers, for the management of the institutions. However, there are also several challenges. First one is the transforming raw data into structured dataset which are convenient of machine learning approaches, and this problem is identified in the various previous research papers. In addition to that, there are other challenges for data analysis from methodological perspective. For example, the lack of model evaluation and holistic approach in selecting the best predictive models. Also, some of the papers written a few years ago emphasize the need to consider features that have temporal properties in order to develop quality predictive models. Let me now explain basic steps of development of a framework for our intelligent system. We have used CRISP-DM methodology standard to develop such a framework. So in the first step, in the domain understanding step, our focus was on the two domains I explained here, and we have included the domain experts as project researchers that provide and will provide in-depth explanation of requirements of each domain. In the data understanding phase, we are performing data collection. So we have some data, but filling up repositories research that is going on. And in the domain of business, as I said, we are primarily using global entrepreneurship database, but also World Bank Group entrepreneurship survey, and also we are performing data collection of our own. Some of the data sources in the domain of education are data from early learning systems of educations which are involved in the project, and also lots of surveys that we have conducted among datasets and publicly available repositories. What we want to do here is to capture all possible combinations of meta features. Thus, we need a lot of data sets in our repositories. Then meta features are identified and categorized for each feature. For each meta feature, we will have minimum of 2 categories. As I said, we need a large number of data sets to be analyzed in order to capture all combinations of meta features. We will develop, and we have developed so far a few predictive models based on different approaches to machine learning. We are using this categorization of 4 machine learning approaches: probability-based algorithms, error-based algorithms, information-based algorithms, and similarity-based algorithms. And we will use at least one of machine learning algorithm from each of the group. So on each of the data set, all 4 approaches will be used. During the evaluation phase, we will try to see which model meets the business objectives, and we will use, of course, standard measures like confusion matrix, level of precision, response. And our results will be integrated into a metadata set which of course consists of meta example. Each meta example consists of meta feature and of course target attribute, which is ranking of machine learning algorithms. One of the most important parts of this intelligent system, of course, is development of meta models. And here we will use different approaches in the development of meta models. One is based on correlation and ranking. Those are simple approaches. Then we will use more sophisticated approaches, which are based on multi-criteria modeling. And here we will use commonly used analytical hierarchy process method, but also novel method developed recently, like SNAP method, which shown to be give a very good result. And of course, we will use supervised learning algorithms for development of meta models and to see which of these approaches gives us the best results. Of course, the meta models will be evaluated, and the best meta model will be built into the final version of the intelligent system. As you can see here, it is really extensive research, and there is a lot of work still to do on the path of this system. And at the very end, here you can see the framework of our intelligent system, which is only conceptual framework, summarized everything I talked about today. So we need to have a large number of data sets in the repository from the two domains, business and education. Based on the features of such data sets, which will serve as inputs, and models, predictive and descriptive models will be performed to see algorithm performance measures which serve as output. So this will serve as our metadata, based on which we will develop meta models in order to select the best algorithm for the data set of specific characteristics. So just to conclude this talk, what we are trying to do in this project is to find the recipe and to facilitate the selection of machine learning algorithm in the special field of social sciences, actually in the two domains of social sciences, education and business, which are really interrelated and connected. Thank you very much for your attention.